Okay, this is going to be a first in a series of videos on Chapter 4, and I like to limit these to about 15 minutes or less. So, first video, I'm just starting right now, it's going to talk about two-way tables and probability. And as you get into the chapter, there's going to be different ways we can calculate probability. And one of the first ones is just the probability of an event. Let's say I want the probability, for example, of Ford here. Well, it's a number of ways that you can have a Ford, which would be the total of Fords in this sample. Just pretend this is a sample of your surveying people who have Ford, Dodge, Chevy, and what color the vehicle is. Okay, something simple like that. So if I ask what's the probability of a Ford, well, there's a total of 190 Fords out of a total of 570 vehicles, or items, or whatever. And if I scroll this up a little bit, you'll see right there, 190 divided by 570 is approximately 0.5 or 0.33. So that would be the probability of randomly drawing one of these people who have a Ford. If I go into yellow, probability of a yellow, well, probability of yellow, 160 yellows out of 570. And you could look at these other two, but you kind of get the idea of what's happening. We're taking a category total divided by a grand total. Okay, that's one way of doing probability. This is for a two-way table. And we'll come back to the two-way table idea in a second. Take a look at my screen, and I'm going to hold up a die. Okay, so it's probably hard for you to see, but I'm not going to blow up my picture. This is a 30-sided die. Okay, so there's 30 different sides. And if I'm assuming it's a fair die, which we have to assume it's fair, if I roll it, what's the probability it comes up on any particular side? Well, there's 30 sides. Any particular one, like a 27, that's going to happen 1 out of 30 times if it's a fair die. So that'd be 1/30th would be the probability. If I change it up a little bit, if I ask what's the probability that I get an even number, well, that should be 15 out of 30, or 0.5, 50%, because there should be the same number of even and odd sides on this. Okay, 15, 15. If I use a 6-sided die, a little simpler to think about. We have sides 1 through 6. If I assume it's fair, which I have to tell you that, otherwise we don't know what's happening. If I roll this, the probability that I get a 1 is 1 out of 6. The probability I get a 6 is 1 out of 6. The probability of any of these particular sides coming up is 1 out of 6. That's probability. Now, I'm going to kind of jump around in a few different concepts in this video. Here's the next one. If I take this fair 6-sided die and roll it, and it comes up on a 1, and I pick that die up and ask what's the probability that I roll it now and get a 1, it's still 1 out of 6. I could do that 100 times in a row, and every time I pick it up, regardless of what the outcome was, the probability of the next one is still 1 out of 6. When you see people that go into a casino and they do the slot machines, and they're feeding the slot machine, they're operating on the assumption that it's going to have to pay off if they do it long enough. The reality is, the probability from one turn to the next of a particular outcome is always going to be the same if those events are independent. And the key word there is independent. Each roll of this die, or any fair die, is independent of the next. Even if it's an unfair die, it's still independent of the next. If I say the probability of a 1, if I load this die for some reason, and I say the probability of a 6 is 50%, that means 50% of the time this is going to land on a 6. It doesn't mean it's fair, but every time I roll it, the probability of a 6 is still going to be 50%. They're independent. Independent means knowing that something has occurred has no effect on the next trial. Flipping a coin. Now, I don't have a coin with me at the moment, but if I take a coin and flip it, fair coin, probability of head is 50%, probability of tail is 50% if it's fair, but one flip to the next has no effect. I could take that same coin, flip it 10 times in a row, get heads every time, and the probability that it's head on the 11th is still 50%. Now, is it very likely that I'll get all heads? No, but there's still probability that that can occur. And you have to keep straight the probability of the next event, if they're independent, does not change. if I look at cards. Okay, so a deck of cards. And I like cards because supposedly everyone knows cards, but I'm finding less and less do over the years. You should know how many cards are in a deck. 52. You should know how many suits. There's 4. You know, what's a face card, all that. So I'm just going to keep this simple. I'm assuming all 52 cards are here. So what's the probability, if I shuffle, okay, it's all shuffled, what's the probability that I draw an ace out of this deck? Well, how many aces are in a deck? Okay, so it's 4 out of 52. And you can reduce that down to 1 out of 13 or change it to a decimal, whatever. So now I'm going to draw a card. Okay, here's a card. And it looks like the 6 of hearts. All right, now if I take that card in my deck and put the card back in my deck and shuffle it all up, okay, it's shuffled up. I'm not trying any tricks here, it's all shuffled up. What's the probability I draw an ace now? Well, it's still 4 out of 52, and you can reduce it if you want, but it's 4 out of 52 because I put that card back in. But if I draw another card, 9 of diamonds, and I drop it, okay, that's no longer in the deck. What's the probability I get an ace on the next draw? How many aces are left in the deck? Well, there's still 4. How many cards are left in the deck? 51. So the probability of an ace is now 4 out of 51. And those are no longer independent because I did not replace that card. When you see wording like with replacement, that implies independence. If you see wording without replacement, that implies dependence. Now, I know I'm going fast. You might want to pause it, go back over it. But let's go back to this table. And if you haven't printed this off, you just might want to print these notes off and then continue the video. And we're going to keep referring back to this chart. So come down here and I say, time for some harder ones. Probability of blue or yellow. So blue or yellow. Well, that means what's the probability that I draw something and it's blue or it is yellow. Well, there's 120 blues and there's 120 or 160 yellows, so probability of this or that would be the total of what, 280 out of 570? And that's what should be happening here. But if I also ask the question, probability of blue and a yellow, so in one draw, I'm going to go into these people's files and I'm going to draw one of them. What's the probability that person has a blue and a yellow if they only have one item in this? That can't happen. It can't be blue and yellow at the same time. So that would be 0. The probability of something that can't happen is always 0. You have to remember that. Probability of something that cannot happen is 0. The probability of something that's going to happen is 1 or 100%. Probability of blue and Chevy. That means I want a blue Chevy. I come back up here. Probability of blue and Chevy. I mean the intersection. I'm going to highlight it right there. There's 30 of those. That's blue and a Chevy at the same time. So 30 out of 570. That's an and. Get down here. Another one. Probability of Dodge and green. So I want a green Dodge. Green Dodge would be 40 out of 570. Ford and pink. Well, you can look at your table. There isn't a category for pink, so that can't happen. Can't be both at the same time. So none, 0. Okay, now this one's a little trickier. I'm going to scroll this up a little bit. Concentrate on this line right here. Probability Ford or green. So it's probability that you have a Ford or it is green. So if I look at that, probability is a Ford. Well, there's 190 Fords. There's 140 that are green. Now notice how I do this. Across them here, there's 190 total of these numbers. And there's 140 total of these numbers. But if I add the 140 and 190 together, that's not going to work because you're counting 20 twice. So in your book, they're going to talk about a sum formula, addition formula. And what it is, okay, probability of this happening plus probability of that happening minus probability of the intersection. Or, I kind of like thinking this way. I'm going to take my total for Ford, my total for green, and subtract the overlap and divide by 570. So I would pause this right now and go back through that idea, maybe play around with a couple others. But whenever you're doing an OR, that means you're adding, And sometimes this intersection is 0, and sometimes it's not. When it's not, you have to subtract the 20. Conditional probability, well, you've already done a couple of them. So if I look at this conditional probability, this means probability A given B. Remember the cards? So what's a probability that I have an ace of spades given the first card drawn was not an ace and I didn't replace it? That's kind of how this notation is working. B is what has occurred or a condition of A occurring. And you can rewrite it in this form, probability A and B divided by B. If I look at it in our terms of our table, probability is Chevy given it's blue. So you could look at this, but I'm going to go back up to the table. Probability that you have a Chevy given that it must be blue. As soon as I condition on it being blue, I'm in this column. It has to be blue. What's the probability of a Chevy given it's blue? Well, that would be 30 out of 120, or about 25%, 0.25. Pause it, think about that. Here I'm doing it via formula, and you're going to get the same answer, and I would go through that as well. But you can also think of this as just what I did. Here's another one. Same thing. Zero in on it a little better. Look at this method. So probability of probability of Chevy given as blue, I concentrate on what I'm given. I look for the particular thing I want, 30 out of 120. Here's another one. Let's try another by formula. Well, probability red given Dodge, you have to look up probability red in Dodge. I'm saying it's 30 out of 570. Go check that. Probability of a Dodge is 160 over 570. Check that. Do whatever you do, razzle dazzle, however you simplify it, should come out to be a 0.19 after I round. But if I do it via table, probability of red given a Dodge, I'm given Dodge. That means I'm stuck in this row. Okay, I want the probability that if I'm stuck in this row, what's red? Well, 30 out of 160. So 3/16. And if I scroll on down, 30 out of 160, 0.19. All right. How to show things are or are not independent. It's all right here. That's what I'm going to concentrate on. Read it, look at the example, whatever, but concentrate right on what I shaded. This is saying the probability of A given B has occurred is equal to the probability of A. Well, if these probabilities are the same, then that's telling me that the probability of A does not depend on B, because you're saying the probability of A is equal to exactly the probability of A given B has occurred. So it can be difficult to show things are independent. It's not that difficult to show things aren't. And if I go through this example here, are the events red and Dodge independent? I would always check probability red given Dodge. Well, we did that somewhere. We got 0.19. The probability of just a red is 20 out of 570, which is 0.04. If these probabilities are different, that means that red is dependent on Dodge. They're not independent, they are dependent. And you can go through this example here. Let me move that over for a second. Probability of ace on the first draw is 4 out of 52, 1/13. If I replace the card and draw again, probability of ace on the second draw, given the ace on the first draw, is still 1 out of 13 because you put that card back in. These would be independent because I'm using the keyword replacement. Now I know that's fast. I'm trying to keep this under 15 minutes. Pause it, go back through it, and if you have a question on it, let me know via email or at a Zoom meeting. All right, have a good day.